Hi, Math 30s. We're moving on to Lesson 7, which is called Double Angle Identities. Just like with Lesson 6, I am going to be doing the examples in the workbook along with a few of my own examples. A blank copy of those examples can be found on the Google Classroom. Where I want you to start is I want you to start by taking out your formula sheet, and I want you to notice where the 5 double angles are. So these are the 5 identities for the double angles. What is the reason why we call it a double angle? Well, if you look at the argument, each argument is doubled. So the angle in each argument is doubled. That's what makes it a double angle identity. One thing that I want you to notice is for sine, so the double angle of sine, there's only one identity or one form for the double angle of sine. Cos becomes a little bit more tricky because for the double angle of cos, there's actually 3 forms. So there's 3 identities that we could choose from to use. So there's 3 forms for cos, and then the double angle for tan, there's just 1 form. How we're going to start this is we're going to start by doing a couple of proofs using double angles identities. So we're going to start by proving this identity. So on the left-hand side, I see here a double angle identity for sine. So if you look at your double angle identities, this is the double angle for sine, and that matches up with this form here, and I could take that and replace it with the identity, which is the 2 sine of theta cos of theta. There's a 1 in front. So I'm going to bring down that 1 plus, and I'm going to change this for the identity again, which is 2 sine of theta cos of theta. Okay, then I'm going to look on my right-hand side. What I have on my right-hand side is I have a binomial that's being squared. So let's deal with this binomial being squared by writing each bracket twice. So that would be sine of theta plus cos of theta times the sine of theta plus cos of theta. I'm going to look at both sides. There's nothing really I could do on this left-hand side because there's no quotient identities or reciprocal identities. So I'm just going to leave this as is, and I'm going to deal with the right-hand side. On the right-hand side, I'm going to get rid of the brackets by doing the distributive property. So sine times sine is sine squared of theta. And then sine times cos, you'd have sine of theta cos of theta. And over here, you would have sine of theta cos of theta. So that would give you plus 2 sine theta cos theta. And then at the end, I would have plus cos squared theta. From this point, what I want you to notice is I want you to notice that on the left-hand side, I had a 2 sine theta cos theta, and on the right-hand side, I have a 2 sine theta cos theta. So right now, these two are matching. So what I'm going to do is I'm going to ignore this because that matches with the left, and I'm going to look at or this. Sine squared theta plus cos squared theta. If ever you see a squared, you need to clue in that you have to look at your Pythagorean identities. And the Pythagorean identity is the sine squared of theta plus the cos squared of theta is equal to 1. So what I could do is I could remove, I could put in the identity for the sine squared of theta plus the cos squared of theta, which is 1. And then I'm going to bring down that 2 sine theta cos theta. And now if you look, the left-hand side of my equation is equal to the right-hand side. So left side is equal to the right side, and I've proven my identity. The second proof that I want to do is from your workbook. So this is class example 1 on page 642. It says prove the identity, and then we're going to state any non-permissible values. So when proving this identity, I sort of look at both sides. On the right-hand side here, I recognize that this is a double angle for sine. The double angle for sine, remember that there was only one form for the double angle of sine, and that was this form here. So what I'm going to do is I'm going to replace the double angle of sine with its identity, and the identity was 2 sine of x cos of x. There's nothing I could do here. There's no tans to swap out. There's no Pythagorean identities. I'm just going to stop, and now I'm going to look at what can I do on the left-hand side. So tan of theta, you need to recognize is the quotient identity. So we always want to get rid of our tans or cotans, secants, cosecants, things like that. So tan of theta, like I said, is a quotient identity, and that is the sine of theta, sorry, the sine of x over the cos of x. If you look at the denominator, 1 plus the tan squared of x, one of the tips I had given you in a previous video is if ever you see something squared and a plus or a minus 1, check to see if it's a Pythagorean identity. So I've actually got the 3 Pythagorean identities down here. 1 plus the tan squared of x, it is a Pythagorean identity. The identity for that is the secant squared of theta, or secant squared of x. So what I'm going to do is I'm going to replace this with the identity. I'm just going to write it like this instead of as a stacked fraction or complex fraction. 1 plus the tan squared of x is equal to, down here, the identity is the secant squared of x. Okay, 2 sine of x over cos of x. I can't do anything with that at this point. Divided by, I'm going to put in the identity for the secant squared of x, and secant squared of x is a reciprocal identity, and that would be 1 over the cos squared of x. Now I'm just going to reciprocate and multiply. So the first fraction is 2 sine of x cos of x times the reciprocal of this fraction, which would be cos squared of x over 1. What you need to see is, because we're just multiplying fractions, I could multiply everything in the numerator over everything in the denominator. And what you will have is you will have 2 sine of x cos squared of x all over cos of x. And then I could cancel out this cos of x. There's 2 cos of x's in the numerator, so I'm going to cancel one of those. And what I am left with is 2 sine of x cos of x. And if you look, that is the exact what we had reduced the right-hand side to, 2 sine of x cos of x. So I've just proven my identity because the left side of the equation is equal to the right side. So that would be my proof. Let's look at the non-permissible values and how we would write the non-permissible values in terms of a general solution. So remember that for non-permissible values, you want to look at fractions. The denominator you could never divide by 0. So here's a fraction. This could never be a 0. So what the non-permissible value would be is the cos of theta, or sorry, the cos of x cannot be equal to 0. So now I have to say where on the unit circle is cos 0. So where are your x coordinates 0 on the unit circle? And that would be over here at pi over 2, because this coordinate is 0, comma 1, and down here at 3 pi over 2, 0, comma negative 1. So where my x coordinate is 0 is at pi over 2 and 3 pi over 2. So that means that my angle x cannot be equal to pi over 2 or 3 pi over 2. And then what I'm going to do for non-permissible values in identities, you always want to be able to write it as a general solution. So the general solution, it falls on the straight line. I'm going to take the principal angle of pi over 2, and every time I add pi n, I will get to the next non-permissible value. So the general solution of this would be x cannot be equal to pi over 2 plus pi n, where n belongs to the element of the integers. Now, one more thing I want to point out is I had said, okay, you can never divide by 0. So some students will say, okay, well, can we take care of this? This can't be 0, which is correct, but I'm going to show you what happens. This is 1 plus the tan squared of x, and that cannot be equal to 0. If I said, isolate your ratio, isolate your trig identity, so isolate tan, we would have the tan squared of x cannot be equal to -1. And then if you were to isolate tan by getting rid of that square, you're going to square both sides. And what happens is you know you can't take the square root of a negative number. So what that means is there are no non-permissible values for 1 plus tan squared of x. There's no angle for x that you could put in that would make this a 0, okay? So the only non-permissible value was for cos of x couldn't be equal to 0. Let's look at this proof, which is another double angle. And the reason why I like this one is because it has two different double angle identities, and now we're going to look at the double angle for cos as well. Okay, so looking at this, I'm actually going to start on the right-hand side. So I'm going to start at that negative cotan of theta, and just recognize that that is a quotient identity. And the quotient identity for cotan is cos of theta all over sine of theta. Nothing else I could do on the right-hand side. I've got to now go to the left. My numerator is the double angle for sine. This was the double angle for sine, that was the form. And the identity for the double angle of sine was 2 sine of theta, cos of theta. So I'm going to take this out, and I'm going to put in its identity, which is 2 sine of theta, cos of theta. That is all over this denominator. And what you need to notice with the denominator is I have another double angle. It's a double angle for cos. So then I have to say, okay, I have 3 forms for the double angle of cos, right? Which form do you use? The answer is you could actually use any of these 3 identities, and you will just have, some will have more steps in simplifying than others. So what I'm going to do for this example is I'm just going to, I'm going to choose this third form, this identity here. And I'm going to take the cos, the double angle of cos out, and I'm going to replace it with 1 minus 2 sine squared of theta. So 1 minus 2 sine squared of theta. And I'm going to bring down this minus 1. Okay, so let's see what happens when we combine like terms, simplify, things like that. Numerator, 2 sine of theta, cos of theta. Denominator, what I hope you can see is you have 1 minus 1, which will cancel. 1 minus 1 is 0, so I'm just going to get rid of that. And I'm going to bring down that negative 2 sine squared of theta. What I could cancel now is the 2's will cancel. And this sine of theta will cancel with that sine of theta. So what I am left with is the cos of theta over negative sine of theta. And if you look at the right-hand side, that's exactly what I had on the right-hand side. So I've finished my proof. The left side of this equation is equal to the right side. Okay, what I always tell students for this question, it's a really good question to redo. So a lot of students, they sort of want to perfect these double angles. They just want to do really well. So I have just, for this, in this video, I have replaced the double angle for cos with this identity here. What you should do later on when you're studying is redo this question and take out, say, the double angle for cos and replace it with this identity. And what you will see is that you will get to the exact same answer as this. And then you could do it a third time if you want, right? You could replace the double angle for cos then with this last one. And again, you will get to the exact same answer. You will just be manipulating and changing out different forms. Okay, I have one more proof here, and I'm actually not going to solve it for you, but the video for this being solved, it is podcast lesson 14C. This is a really good example, so you will want to be able to do this example. You want to be able to prove this. If you can't do it on your own, you could watch that podcast. Let's now move on to the workbook. So the workbook, we're going to do class example 2 and then finish off with class example 3. So what we're going to be doing in class example 2 is we're going to be learning how to write something in terms of a double angle. So what it says is it says use the identity, and it gives you this identity here. What you have to just see is that this is the double angle for sine, right? So on our formula sheet, that was the double angle for sine, and this was its identity, right? So use this identity, and what they want me to do with this identity is they want me to take sine of 6x and turn that into a double angle. How could I take the sine of 6x and turn it into a double angle? Here's how we would do this. Write down the sine of 6x. In order to get that into a double angle, we know that all of our double angles have to have a 2. So I'm going to write the sine of 2. Then, what would my alpha be? So in order to figure out my alpha, I'm going to take 6x. If I divide 6x by 2, I get 3x. And what I have just done is I took the sine of 6x and I've converted it into the double angle for sine. Because 2 times 3x will give you the 6x, but as soon as you have a 2 in front, it becomes a double angle for sine. So now what I could do is I could use the form for the double angle of sine, and I could replace it with the identity. What you have to just recognize, though, is that this is my alpha. So the identity is 2 sine of alpha cos of alpha. So that would be 2 sine of 3x cos of 3x. Let's look at B, which is going to be the exact same thing. So it's just going to give you more practice. Okay, it says write the double angle for cos of 10a. So they want this cos of 10a to be written as a double angle. So I know to get a double angle, I need a 2, right? As soon as I have a 2, it's going to be a double angle. And then what is my angle going to be? So what is alpha going to be? Well, 10a divided by 2 is 5a. That is what alpha is. So what I've just done is I've converted the cos of 10a into the double angle for cos. Now I could plug this into one of the identities. So I've got 3 forms for the double angle of cos. I could do either of these 3 identities. I'm just going to put everything into the first identity. So it would be cos squared of alpha. So cos squared of 5a minus sine squared of 5a. Okay, let's look at the second one, which is the tan of x. So the tan of x, this guy is going to be a little different, a little bit more complicated. And we're going to go through it because this is going to be a homework question, and this is just a bit higher level of thinking than this one. So what we need to realize is you need to realize that there's a 1 in front of here. So that's the first thing I'm going to do is I'm going to put that 1 in. So this is the tan of 1x. They want me to convert this into a double angle. So you say, okay, I'm going to do what I've been doing. That would be the tan of, I need a 2 here. I need to double my angle, right? Because double angle identities, we need to have a 2. Then I need to figure out, well, what is my angle? So in all of these previous examples, in order to figure out the angle, we've been taking this argument and dividing it by 2, right? I took 6x, I divided by 2 to get my new angle. So I'm going to take this argument and I'm going to divide it by 2, which would give me 1 over 2x. That is now alpha. Once I have that now, I could write the identity for the double angle of tan. So what that would be, it would be 2 tan of alpha, which is 2 tan 1/2 x, all over 1 minus tan squared of 1/2 x. Okay, and that's how you would write as a double angle. So why do we do this? Why are we writing as a double angle? Where this is going to help is later on when we're solving and we're solving for an exact value, you will want to switch out, let's say the tan of x or the cos of 10a into its double angle identity so that you could find the exact value of something. So that will be in the next lesson when we're going to start solving. Okay, the last class example we have is class example 3. We are doing essentially the opposite of class example 2. So if you look at this, um, what's going to happen is as you do homework examples, you're going to start recognizing things. So I always, like I have memorized because I've done it so many times, whenever I see a 2 sine cos, I know that's a double angle for sine, okay? So if you were to match this matches up with this identity here, and what you have to realize is you have to be able to identify, okay, well, what would alpha be? So alpha is 4x. So that is the identity for the double angle of sine. So that would be equal to the sine of 2 times alpha. Alpha is 4x. That is equal to the sine of 8x. And that would be my answer. My answer is going to be the sine of 8x. What I just want to show you is I want to show you how we could go again from here, which was class example 2, back here if you really wanted. So again, if I gave you the sine of 8x and I said write that as a double angle, you would say, okay, I need to have, if they wanted as a double angle, I need a 2, right? What does alpha become? 8x divided by 2 is 4x. This would be my alpha. You would then take this double angle for sine, and you would use the identity for it, and you would get back to exactly where we started. Let's look at B. Cos squared of 1/2 a minus sine squared of 1/2 a. This is going to be a double angle identity, and it's going to be a double angle identity for cos. Now, one thing I just want to point out, sometimes students make a mistake with this, and they think it's actually going to be a Pythagorean identity, because remember that the Pythagorean identity was cos squared of theta plus sine squared of theta, and then if there was a plus here, I would be able to write the identity for that, which would be 1. But because there's not a plus, right, there's a minus, it is not a Pythagorean identity. This is going to be a double angle identity. And again, matching this up, this is the double angle identity for cos, and it would be this form here. Okay, so this is equal to, let's just identify alpha. So that's alpha, and this would be alpha, right? Because when it's in the form of cos squared alpha, this would be my alpha. The argument would be alpha. Okay, so that's the double angle of cos, so let's write that down. That would be the cos 2 and then alpha. Alpha is 1/2 a. From here, let's simplify, and 2 over 2 is going to cancel, which will leave us with the cos of a. Let's do this last class example, then I'll give you your homework, and I'm actually going to set one question up for you in your homework. Class example 3C. You're going to star this. This one is a little bit tricky. Again, you're going to see this in your homework, but this is a really good question to test higher level understanding for this. If you look at this, what you will see is you will match this up and you'll say, okay, this is really close to being a double angle for sine, right? So this form is very close to this identity here. But what you'll notice is, well, this 2 is missing. In order to make it a true identity, I need to have a 2 in front of this. So I'm going to just put this 2 there because I want it to match this form, okay? So let's just actually write that. So 2 sine of 5 over 2x cos of 5 over 2x. Now it matches this form. But here's the thing. You can't just decide in math to add a 2 out of nowhere, right? You can't do that. What you need to do if you want to do that is you need to balance it. So how could you balance the 2 that you added? You would balance it by multiplying this by a half. And the reason why that's how I would balance it is because what I originally started with was a 1, right? I put the 2 here to make it the double angle because I'm going to be taking this out now and putting in the identity for this. But in order to put the 2, I needed to balance it by 1/2. If I, though, multiply 1/2 by 2, I get to what I originally had, which was a 1. Okay? So to introduce a 2, you could do that, but you need to balance it by multiplying it by 1/2. The reason why we were doing this is because you would then say, okay, this is the identity for the double angle of sine. That's what it would be the identity for. So I'm going to take this out and I'm going to put in the double angle for sine, which would be the sine of 2 alpha. And what was alpha? Alpha was 5/2x. Now, what you need to do though, this was the identity for my double angle. I cannot drop this 1/2. I need to bring that 1/2 down. The most common mistake that students will do is they will drop that 1/2, right? And they'll just have sine 2 and the angle being 5x/2. Do not drop that 1/2. That was what we needed to balance the expression. I could clean up something in my argument, and what I could clean up is 2/2, and that would give me an answer of 1/2 sine of 5x. Okay, so that is the class examples. We're going to talk about the homework, and then I'm going to set up one of the class examples with you. So the homework for this is on page 643. I want you to do these questions here. These last 2 questions, these are standard of excellence questions, and sometimes students get stuck on, okay, well, how would you solve this? Both of these questions are podcasted, so you'll have to go to the podcast for Trig 2. The title of this question, though, it's Diploma Question 7. So look for your diploma questions. Open up diploma question, the video for diploma question 7, and you'll see this question. And then for number 9, if you get stuck, open up diploma question 8. If you're wanting to watch other podcasts, 14C was a proof, 14D I'm actually going to take care of in the last lesson, lesson 8, and then 2 more diploma questions. Okay, I want to just start question number 2 with you. So if you want to flip to your homework, and I'm just going to look at question number 2, which is right here. So write the double angle identities for the tan of 6x. So again, we did this in class example 2. If you are writing the tan of 6x as a double angle, in order to have a double angle, you need to have a 2 here. And then what does alpha become? Well, 6x divided by 2 is 3x. Now you're going to use the identity, right? So you're going to look at your formula sheet, you're going to look at the double angle for tan, and you're going to write that out. Every time you see alpha, you're going to put 3x in. Let's do this one. So the cos of 3 theta, write that as a double angle. How would you do that? In order to become a double angle, I need to have a 2. That's what makes it a double angle. And then how did we find alpha in each of these questions? We took the argument in the original and we divided it by 2. So the argument was 3 theta over 2. This is now the double angle for cos. Let's identify what alpha is. So that would be alpha there. And then from there, you have to put it into one of the identities. Remember, cos had 3 forms. The solutions put it into the first form, the one that was cos squared alpha minus sine squared alpha. So that's the one that they're going to plug it into. Let's do C together. And I'm going to star C. Turn sine of 1/2 A into a double angle. So sine. We need to have a 2 if we want that for a double angle. What does alpha become? Well, what we've been doing is we've been taking our arguments and we've been dividing them by 2. That is the exact same thing as 1/2 times the reciprocal of 2, which is 1/2. A half times a half is a quarter. So if I took this argument of 1/2 a and I divided it by 2, what I would get is 1/4 a. And that would be your alpha. You now have the form for the double angle of sine, and you just now need to plug in um, using your identity for the double angle of sine. Okay, that's all I'm going to show you, and hopefully that explains it.